I want to draw a force or a free body diagram to model all the forces involved in all the objects. So let me just make a little sketch of the situation over here. Here's my table, here's the earth, and here's the book sitting on the table. Makes sense? That doesn't help me very much. I'm trying to analyze the forces. So in a free body diagram, you represent every object as a dot. I want to represent all the objects here with a separate free body diagram, every object in your system. That's an important word. I don't think we've used it yet. The word system means whatever you are studying at the time. So what objects are in our system? Well, our system is right here. It is the book, the table, and the earth. That is our system. That's what we're studying. That's the scientific system that we're studying. So every object in your system gets its own free body diagram and gets represented with a dot. So let me think about, first of all, the book. So I'm going to represent the book with a dot. I'm going to label it maybe as book. And I need to think now about all the forces that are acting on this object. Remember, a force is a push or a pull that has the potential to accelerate an object. This is going to take some practice, and you just have to kind of learn about the different forces involved. But I want you guys to apply some knowledge that you probably already have. This is very close to the surface of the Earth, the book is. So what force, first of all, can we think about that is probably being applied to the book? It's the force of gravity, which we discussed earlier, and we will discuss in more depth later in this unit in a few modules. You guys know the force of gravity always faces downward. So I'm going to draw a line just like this. And I need to label this force now. This force I'm going to label with a capital F. Every force in my diagram will get labeled with a capital F. And then I need to label the type of force. There are several different ways of doing this. I know that this is the force of gravity. It's the gravitational attractive force. So I'm going to label this with a lowercase g, force of gravity. And then I'm going to do something called labeling the feeler and the dealer of the force. What is feeling the force? What object is feeling this force of gravity right now? The book, right? So I'm going to label a B for book. I'm going to write a comma. That is the feeler. The book is feeling this force. What is dealing the force? What is giving the force? Where is that force coming from? What is affecting this pull down? The earth. The earth's huge mass causes this gravitational force downward. So I'm going to label the dealer here with a lowercase e, the earth. There's my feeler and my dealer, the force of gravity felt by the book, given or dealt by the earth. That is a comma separating them. And that's exactly how these diagrams are going to work. What other force is involved? Notice that if I were to leave this diagram just as it is, I have what is known as an unbalanced, unopposed force right here. I just have a downward force. There's nothing opposing it upward. So the only thing, there's nothing opposing it upward. So there is a net force. My net force would be down. There's nothing canceling this out, in other words. So what would happen to the book? It should be accelerating downward. It would have a downward acceleration because we know that a net force results in acceleration, Newton's first and second laws. So there has to be another force opposing the force of gravity. Think about the situation. The book is on the table. So is there another force? Yeah, I think we can say that the table is pushing the book up. And notice how I'm going to draw this arrow. I'm going to draw this arrow as carefully as I can to try to show that the upward force and the downward force are the exact same size. Why do I need to do that? Because those forces are canceling each other out. Is my book accelerating? Is it changing its motion? No, it's resting. The book rests on the table. It rests. It has a velocity of 0. It has no acceleration. So if the acceleration is 0, let's think back to Newton's second law. The sum of all the forces acting on the object equals the mass times the acceleration. Well, I know that the acceleration is 0 in this situation. The book is resting. So what does the sum of the forces have to be? The sum of the forces must be 0 as well. 0 times the mass is going to be 0. These forces will add up to completely cancel each other out. Think about this. If I were to take these two arrows and draw them side by side, I have one arrow going up. Remember, forces are vectors. They have a direction. Maybe I could call that the positive direction. In fact, just for an example, let's give these numbers. Let's say that this force is a force of positive 5 newtons. We will do mathematical examples later. Well, my force going down, I know it has to perfectly cancel out. So what would I label this force as? Negative 5 newtons. They cancel out. Positive, this force is going up, and then this force gets me right back to where I started. I don't have any resultant. I don't have anything left over. There's nothing left over. Positive 5, negative 5, that is a total of 0. That is what this means right here. The sum of the forces in my example would be positive 5 plus a negative 5 equals 0. The sum of the forces is 0. I know that because the book is not flying up in the air. It's not accelerating upward. It's not accelerating downward. It has no acceleration. The acceleration is 0, so the net force must be 0. Those forces must balance each other or cancel each other out. I would call these balanced forces or canceled forces. They cancel each other out. I don't have anything left over. Notice too how I'm using the positive and negative sign just like we have for any vector that we've been studying. Positive and negative show direction. In this case, I'm using positive to mean up, negative to mean down. You can really choose whatever direction you like. I could have said that up is negative, down is positive. I would have gotten the exact same result. It does not matter as long as you are consistent. Anyway, I have not labeled this force yet. I know they're equal because the net force has got to be 0. So let me label this force. This is a force. And what type of force is it? Well, whenever things are touching, I like to call those forces contact forces because the things are in contact with each other. Contact forces. It's a force of contact. Now I need to label the feeler and dealer. I'm analyzing the book right now. So my feeler, what's feeling that contact force? It's the book. Your feeler, whenever you label the forces, will always be the object that you're analyzing at that time, the book. What is dealing? What is giving? What is affecting that contact force? The book is resting on the table. The table is pushing it up. So where's this pushing force coming from? Where's this upward force coming from? The table. So there is a free body diagram for the forces acting on the book. Let's do the table now. And what force is the easiest one for us to label right now? Is this table close to the surface of the Earth? Yes, it is. So it is affected, as we've discussed, by the Earth's gravity. So I'm going to have a force going down, the force of gravity. Feeler and dealer. What's feeling that force? The table. What's dealing that force? The Earth. So that's the force of gravity, once again, pulling down on the table. Is there anything else happening to this table? Think about it. Think about the situation. Think about what we did over here. The book and table are in contact with each other. Do you think that the table is going to feel a force from the book? Well, yeah, the book is resting on the table. That book is pushing down on the table. There's a force there, a pushing force. So I need to label that as well. I want you to notice something that I have not pointed out yet, but once again, you always represent the objects with a dot, and your forces are arrows. you always have to put the tail of the arrow on the dot. You're never, ever, ever going to draw it like this, with the head of the arrow on the dot. That cannot be a force going down. That's just not how we label it. We label all the forces with their tails, their flat part, on the object. That helps us clearly see the direction of the forces involved. And sometimes you're going to have more than one force on the same object in the same direction. And that's the case here. If you're paying attention, what else do I have pulling or pushing the table down? I have the book pushing the table down. So I need to draw a force going down. And I know that it's kind of funky to kind of smoosh it in there, but that's what you have to do. And I need to label that force now. It is a force of contact felt by what? Felt by the table. Dealt by what? Dealt by the book. So you can see I have two downward forces on the table. The Earth's gravity pulling it down, the book on top of it pushing it down. Do I have any other downward forces? I don't think so. So is this table accelerating downward? If I were to leave it like this, I would say, oh look, there's a net force down. A small downward arrow, a bigger downward arrow. That results in an overall downward arrow. If I were to add up those arrows, they would both point down. They would both agree and point down. So I would have a net force down, meaning I would have an acceleration down. Is the table accelerating downward? No, it's not. It's not moving. The table is at rest. So what do I have to have? I have to have a force opposing both of these. I have to have a force that balances out both of these. So I have to have an upward force so that the net overall total force is 0. So I'm going to try to make this arrow the length of these two combined. Once again, we can think about it like this. Here's the downward force from the book. Here's the downward force from the force of gravity. I need an upward force that perfectly cancels both of those out and gets me back to where I started so that the overall force is 0. Where is that upward force coming from? Well, where is the table? It's resting on the Earth, isn't it? So I'm going to have a force of contact felt by the table and dealt by the Earth, just like that. So here's a force diagram to show all the forces acting on the table. And this is where it gets interesting. We're really talking about Newton's third law. We're making diagrams that represent Newton's third law. So we want to identify now what I'm going to call third law pairs.